Greetings and welcome to another nostalgic chat. We are busy with IEB's paper 2 from November 2022. Question 11. Prove the following identity. 1 plus sine 2x plus sine squared x minus cos squared x divided by 1 plus 2 sine x cos x plus cos 2x is equal to tan x. Wow, such a bombastic expression ends up being such a simple thing. Okay, so the first thing that stands out for me is that the right hand side is dealing exclusively with the angle x, whereas on the left hand side we have the angle 2x and the angle x. So that makes me feel like, okay, maybe as a starting point, let me try to express all these guys in terms of x instead of in terms of 2x. However, something else that stands out for me is that sine 2x is the same as 2 sine x cos x, and sine squared x minus cos squared x is the same as, well, so I know that cos 2x is equal to cos squared x minus sine squared x. So this is the same as the switcheroo of this, which is the same as negative cos 2x. So I don't know if that could take me anywhere. I think it could. I'm actually curious about that. Okay, so I'm going to try that, and then if that fails, I'll go back to strategy 1, which is to express all of these the ratios that are for the 2x angle, express them as ratios of the x angle. Right, so my left hand side is 1 plus sine 2x plus sine squared x minus cos squared x, and at the bottom we have, oh, that was such a skew line, my goodness. Yeah, really, like, these two strategies are just reverses of each other, right? In the one strategy, we're going from 2x to x. In the current strategy, we're going from x to 2x. So, really, same side, what? Different sides of the same coin. So here we're going to use the fact that, okay, cos of 2x is the same as cos squared x minus sine squared x. Right, so therefore minus cos 2x, we'll switch the difference around. Okay, right, so this is the same as minus cos 2x. Okay, just to highlight again where that is coming from. Okay, right, and then down here we have 2 sine x cos x is the same as sine 2x. Okay, and then plus cos 2x. Okay, so now what I want to do is remember that in order to cancel things, right, you can't cancel if there's more than one term either at the top or the bottom. So what I want to do is I want to get the top to look like the bottom. And how I'm going to do that is I'm going to rewrite this. So I'm going to rewrite minus cos 2x as positive cos 2x minus 2 cos 2x. Right, that does give me a minus cos 2x. So, and then I'm going to see how far that gets me, because now I'm going to have well, 1 plus sine, yeah, I don't think it's going to get me very far, but anyway, let's see how long I can force matters. Okay, so now the perk of doing this is I can say I can split the fraction up a bit. Okay, then this one will become just the cos 2x divided by 1 plus sine 2x plus cos 2x. Okay, yeah, this is a bit of a zero. I think ultimately the solution is gonna lie in going to just x's. I don't see myself going very far with 2x. So I am going to, okay, I'm not going to ditch it. I'm just going to start afresh, and then who knows, maybe I'll be inspired to come back here. Okay, so yeah, operation, let's take it to the x's. Man, all day, every day, I just have cowboy carter songs playing in my head. Now I've got alligator tears on repeat. I don't even think I liked that song, but okay, here we are. The power of Beyonce. Right, okay, so now we want to rewrite things in terms of x and not 2x. So this is using my sine double identity, and then we've got sine squared x minus cos squared x. And then down here we have similar thing, and then I'm going to write it as cos squared x minus sine squared x, just because that kind of looks like the top. Okay, so now we definitely want to cancel things out because we're ending up with one term over here. So it's giving factorising. However, grouping is the immediate technique that comes to mind because we're dealing with 1, 2, 3, 4 terms. So, and there isn't a common factor currently. So, but nah, your grouping is not looking promising because of this little one. Like, it doesn't have anything in common with anyone, well, other than 1. So I want to replace the 1 with sine squared plus cos squared, and see what that gives us. And I'm going to do the same at the bottom. Bottom, what a weird word, or just a weird pronunciation of it. Okay, right, so same at the at the bottom. We're going to replace the 1 with sine squared x plus cos squared x. Okay, and then here we have cos squared x minus sine squared x. Okay, so let's see. Cos squared x is going to cancel out with minus cos squared x, right? It's going to give us 0, and then down here we have sine squared x minus sine squared x. Okay, so now at the top we have 2 sine squared x, we've got 2 of those terms, and 2 sine x cos x. Okay, so it's smelling like I'm going to get a common factor soon. Down here I have 2 cos squared x, and again a 2 sine x cos x term. Yeah, let's see if we take out common factors what we get. We're going to get sine x here and cos x there, and then down here the common factor is 2 cos x, then we're left with cos x plus sine x. Haha, so now the 2's cancel, this bracket is the same as this bracket, so those are going to cancel out, So all we're left with is sine x over cos x, which is the same as tan x, which is our right hand side. Yippee. Okay, the next question says determine the values of x for which the identity given in A is not valid. So said identity, I'm not going to write it out again. Let's just do some creative artistry. Where do I approve my edit? Where's the little, oh, there it is. Okay, right, so that's the identity. So I mean, I'm inclined to say that just looking at the right hand side, it won't be valid wherever tan of x is not valid. However, it is entirely possible that this denominator also brings more restrictions, possibly. Okay, let's see, I don't know. Okay, so looking at the right hand side, we know that tan x is not defined when x is equal to 90 degrees plus k 180, right, where k is some integer, because that's where we have all the asymptotes. Okay, so that's one case. On the left hand side, the identity won't be valid if the denominator is 0. There's nothing interesting happening at the top. Sine and cos are defined for any real value x, so this is fine. But where it could be a problem is if the denominator is equal to 0. So is not defined if 1 plus 2 sine x cos x plus cos 2x is equal to 0. And this expression, it came down to, it looked like this eventually, right, after doing all of our replacing and whatever. It looked like that. Yeah, again, something I don't really want to rewrite. Oh. Now I've got the Miley Cyrus. What's it? I'll be your shotgun, baby. Two Most Wanted playing in my head. Anyway, okay, so either cos x is equal to 0 or cos x plus sine x is equal to 0. And if you look at your cos graph, blah blah, this happens at 90, this happens at 270, and then over here we have a peak at 360, and then it's back at the x-intercept at 450, right? So this is also cos x will be equal to 0 when x is 90 plus k 180. So the same places where tan x is not defined, which makes sense because tan x is equal to sine x over cos x. So tan x, well, is not defined at the places where cos x is 0. So no surprises there. Okay, but let's see if this one is going to bring up anything interesting. So that is cos x is equal to minus sine x We can divide both sides by cos x so that we end up with tan. So that's going to be 1 over negative tan x. So that'll be negative 1 is equal to tan x. Okay, so in terms of quadrants, where is tan negative? It's negative here or here. So, and we know that our ref angle here will be inverse of tan of 1, which is 45 degrees. So x is equal to 180 degrees minus 45 plus K180, right? And remember the K180 is going to get us into both quadrants, right? So instead of K360, and we know this also because of the periodicity of our tan function, right? It's different to your sines and causes because its period is 180 instead of 360. Anyway, right. So, wow, okay, so it does turn out that, yeah, we can't just look at the one side. Must look at the other side as well because, yeah, this is another restriction on, you know, for what values of x this identity will be defined. So let's just consolidate now. So in conclusion, okay, let me just put these all in one place. Okay, so these are the places where the identity is not defined. So I want to see if we can put this into one happy, yeah, just if there's one expression that can encapsulate both of these. I don't think there is, but it's worth a shot. So I'm just gonna look at the positives. So 90 plus 180 is 270, plus 180 is 450, plus 180 is 630, and so it goes. And then for this guy, we have 135 plus 180 is 315, plus 180 is, oh, I'm sweating, 495, plus 180 is 675, and so on. Yeah, okay, we can't really put these together because from 90 to 135 is 45, and then we add 135 to get there, and then 45 to get there, and then 135 to get there, and then 45, and then 135, and then 45. So we can't bring them into one nice little, you know, because it only really works if there's a constant difference between from one term to the next. I'm not doing a good job of explaining this, but I'm also ill. I'm ill. Ugh. Should be sleeping, but here I am with my addictions. So in conclusion, when x is equal to this or x is equal to this, where k is some integer, the identity is not valid. And we can check this. So let's just take a sample from each set of x's. So over here we can take, let's take 90 plus minus 2 times 180. And from this one, let's take 135 plus 5 times 180, right? K is any integer of your dream. So this is 90 minus 360, which is minus 270. and this is 135 plus 900, which is 1035, I think. Okay, so if we put these values into this identity, we should get an error. So let's see. Let's start with negative 270. Complex infinity, my goodness. Okay, so let's try with 1035. Indeterminate. Interesting that there are different. Yes, okay. Interesting that it's different problems. Okay, so indeterminate is because the 1035 makes this equal to 0, right? So then you're dividing by 0, and that gives us indeterminate. Whereas the minus 270, if you think about your tan graph, right, it's just infinitely big because it's approaching that asymptote, never touches it. So it's a different problem to division by 0. I don't know if I'm making sense, but it's just interesting that it comes to it hits a different stumbling block for the two sets of values that we found. But yeah, okay, cool beans. So the moral of the story is, hey man, just check on both sides. There's no harm at all in checking both sides. Cool. Thanks for tuning in, and catch you another time for another ramble. Hey, I just actually want to check that this thing does in fact work for some other random number. Yeah, let's just use 10. So first of all, this should be defined. Go, Kalki, go. Go, go, go. Right? So that's that, and it should be equal to tan of 10. Yes, it is. Okay, anyway, right. Cool. Bye for real.